Hello, Algebra Tours. Today we're going to be talking about graphing exponential growth and decay models. So today is going to be probably a little bit longer of a video than you're used to. And if you're definitely not listening with audio, or if you're starting with audio and you're thinking about shutting it off, please keep your audio on. There's going to be a lot of good explanations where I'm talking a lot and I'm not necessarily writing things down, or I'm just referencing things or pointing to things in order to better explain this topic. So when we talk about graphing these things, what are these things? This is the start of a new unit when we're talking about exponents, and we'll eventually talk about logs or logarithmic functions. But first we're going to start with exponents. So exponential functions or models, like people say this all the time, you guys. Oh, it's growing exponentially or it's declining exponentially. What does that mean? We're finally going to figure out what that means graphically, algebraically in this video. So when we talk about exponential functions, instead of our functions just having an exponent, like we've talked before about like y equals x squared, well, that had an exponent in it. So what's the difference when we say exponential? That means that our exponent is going to be x. So we're going to have some base b, and our exponent is going to be x. So that's where exponential functions come from. Okay, the best way to explain exponential growth or decay is this would you rather question. And maybe you've heard of this would you rather scenario, but this is the best way I can explain exponential growth or decay. Option A, your question is would you rather have option A or option B? Because you want to get the most money that you possibly can. Option A is $10,000 of money is given to you every single day for the next 30 days. So each day for 30 days you get $10,000. Option B is if you received a penny today, for the next 30 days, how much would you have at the end of it if you doubled it every single day? If I gave you double of what you had yesterday, how much money would you have at the end? When you first look at this situation, you're thinking, oh, well, $10,000 today or a penny today, and I don't want to wait 30 days. I definitely think option A is better than option B. But if we do some math, let's figure out what you would have at the end of the 30 days. So option A is $10,000 is added to your bank account, if you will, every single day. So at the end of 30 days, you would have 10,000 times 30 for a total of 300,000, right? Option B, if we double it, at the end of 10 days, we'd have 1,024 pennies. Well, that doesn't seem super promising, but let's go all the way to 19 days. Well, 19 days, we'd have 524,288 pennies. And if we keep doing the math, on day 30, you guys, we would have $21,474,836.48. This right here is what we call things growing exponentially, doubling, halving, carbon dating. All that stuff is exponential functions or things that are growing or declining at a super, 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 super fast rate or big percentage at a constant rate. That's what we're talking about, okay? So that's where we're going for this video. So in your notes, you should write this down. Exponential growth and decay. What is it? Things that grow or decline at a certain rate or percentage. And it usually grows or declines super fast, like we saw with the pennies in 30 days. We went from starting at a month with 1 penny to the end of the month, we're $21 million into money. That's awesome. That's a huge growth percentage rate. Okay, so examples of things that go are like bank interest accounts or bank accounts and your interest. Populations can grow or decline. Uranium radiation declines, depreciation on your car declines, fossil carbon dating is declining as age happens. How much is it deteriorating as time goes on? All these things are examples of exponential growth or decay. Okay, so this is a typical picture of what exponential growth looks like and what exponential decay looks like. Remember how I talked about functions for exponential growth or decay have the x in the exponent? So that's where our x factor is going to be, is in that exponent for exponential functions, all right? So on the left, we have a growth, and notice that my equation is y is 2 to the x, and then notice the base on the decline, it's y is equal to 1/2 to the x power. That's going to come into play later today. So this is visually what those graphs look like when we talk about growth. So this would be growth, and this would be decay. Because as we read graphs, we read from left to right. So it's growing as we go to the right, and here it's declining as we go to the right. So those are what those graphs will look like. So our goals for today are going to be able to graph exponential growth and decay functions on grid paper, to identify the domain and range as we have been with other functions. And then we're also going to learn about this funky word called asymptotes, and we will identify them on our graph. So those are our 3 targets or 3 goals for today. Okay, graphing exponential equations. This is your generic form of a decay or a growth equation. Y is equal to A times B to the x minus h all plus k, where y equals b to the x is your parent function. This is as basic as it gets. And just like every other equation that we've run into, A affects your y values. It's a stretch or a shrink. Sorry, trying to spell shrink. And then h is going to move left or right. And then k is going to move up or down. Just like we've done in the past with cubed roots, square roots, quad lines, we've done quadratics, all that stuff. A is a stretch or a shrink on those y values. H is a left or right movement, and it's always the backward sign, and k is an up or down movement. So we should know that our most basic exponential function is y is equal to some base raised to the x power. If that base, you guys, is greater than 1, that means that it's a growth. So if it's greater than 1, it's a growth function. If it's between 0 and 1, or if it's a fraction, then it's a decay. So if it's between 0 and 1, or greater than 0 and less than 1, or if it's a fraction or a tiny decimal, it's going to be a decay function. So make sure we know what the parent function is, when it's growing, when it's decaying, and what the generic form is, so we can do some transformations on them. All right, so our first example, example number 1, f of x is equal to 3 times 2 to the x. Before we even perform any transformations, let's figure out what my parent function is for this problem. Remember, parent is in the form y is equal to some number b raised to the x power. So my b in this case would be 2 because it's getting raised to that x power. So my parent function is y is equal to 2 to the x. So for that parent function, let's just plug in some numbers. So if we plug in, I don't know, -1, I'm just picking numbers to plug in for x. -1, 0, 1, and 2. If I plug in a -1 into this function, I'll do some scratch work over here. Okay, if I have 2 to the -1 power, whenever you have a negative exponent, or if you plug this into your calculator, you'll get back an answer. We have to move it to the other side of the fraction bar. So that's going to be 1 over 2 to the first, which if you punched into your calculator, you find is 0.5. If I plug 2 to the 0 power in, anything to the 0 power is 1. If I plug in 1 for x, I get 2 to the first, which is 2. And then if I plug in 2, I get 2 squared, which is 2 times 2, which is 4. So this is my parent function. If I go -1, up 0.5, 0, 1, 1, 2, and 2 to the 4th. So that's my parent function. And so if I connect the dots from left to right, that's what it's looking like based on what I know from those pictures that we saw at the beginning of today's video. So if I want to perform the transformations for my new function, y is equal to 3 times 2x, You guys, I don't have a minus h or a plus k on this at all, but I do have a stretch or a shrink. So that means I'm going to multiply my y's by that a value, which is 3, in order to come up with my new table. So my new table, my x's don't change. So that's going to be -1, 0, 1, 2. And my y's are going to be, well, 0.5 times 3 is 1.5. 1 times 3 is 3, 2 times 3 is 6, and 4 times 3 is 12. So it's going to go a little bit off the graph. But if I plot those points, now I have -1 up 1.5, 0 up 3, to the right 1 up 6, and to the right 2 up 12 or so. So if I connect my points here, see how it's stretching vertically on that y-axis? It's making it narrower when we stretch it or pull it apart from top to bottom. So that's what's happening. I'm stretching this parent function by a factor of 3. So for now, don't worry about the asymptote. We'll talk about that. But my domain of my blue function, y is equal to 3 times x 2 to the x, is all reals, or -infinity to +infinity, because I'm not restricted on the left or on the right. And then when I talk about range, I need to figure out from bottom to top. You guys, no matter how many negative numbers I plug into this function, the parent function or the blue function, I'm never going to go negative, no matter how many times I try to plug in a negative value for x, because we have 2 to the x. Whenever you plug in a negative number into an exponent, all it's going to do is put 1 over that crazy big number. It could be 1 over 1,000 or whatever. So all that means is that this is going to get closer and closer and closer and closer to 0, but it's not actually going to touch 0. So what does that mean for my range? That means that it's not crossing the x-axis, which means my range is from 0, that y value of 0, to infinity, to +infinity, if I'm going from bottom to top. Okay? And that's what your graph should look like. So what is an asymptote then? The formal definition of an asymptote is a line that a graph approaches more and more and more and more and more and more, but never truly touches. So like on the last slide when we talked about it, or on this picture, let's talk about this picture, we have a line, y is equal to 3, and this is getting super, 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 super close to it, but it's never actually touching it, even if we think we're touching it. That's what an asymptote is. And that's going to dictate our range for today. So it's going to dictate our range for today, okay? So make sure you get this definition of asymptotes in your notes. Okay, example number 2 is the function f of x is equal to 3x minus 2 all minus 5. 3 to the x minus 2 minus 5. So my parent function for this is going to be y is equal to 3 to the x. And then the -2 and the -5 are my movements that are moving right 2, remember it's the opposite sign, and down 5. But for the purposes of this video not being super, super long, we're going to do this together in class, okay? So you don't have to do anything for this problem. We're going to work on this one together. So just make sure you know what the parent function is, or for this problem, just be able to identify that my parent function that I'm going to start with is just that b to the x. So y is equal to 3 to the x. For the next graph, for example number 3, our function has a lot of stuff going on. We have an a value that's getting multiplied by a -4. We have an h value that's moving left 1, and we have a k value that's going up 3. So if I just try to weed out the a, h, and k, all I'm left with is y is equal to 2 to the x power, just like we had on example number 1. That's my parent function. But just like for example number 2, we're going to do this one together in class when you come back, okay? Because I don't want this video to be too long, and I also know you're going to have a lot of questions, so I want to be able to do these together, okay? Okay, but we are going to do number 4 together in this video. So now I have the equation f of x is equal to 1/5 raised to the x power all plus 1. Okay, so we have to figure out what my parent function is before we even start. So what's my parent function? Remember, parent is y is equal to the number raised to the x power. So for this one, all the transformations we're doing is plus 1, which means my parent function is y is equal to 1/5 raised to that x power. So we are going to just have to make our own little parent table. And you guys, when I make these parent tables, I'm just picking x values that I want to, I guess. I'm just kind of guessing, and then I'm plugging them in to find the y value, okay? So I'm just going to try, oh, I don't know, a -1, 0, 1. Let's see what happens. So if I do my scratch work, if I plug in to y is equal to 1/5 to the -1, if I plug in -1 for x, sorry, if I plug in a -1 for x, so we're raising 1/5 to the negative power, which means that we're flipping that fraction, or we're moving the 5 back to the top, right? So we're saying 1 to the -1 and 5 to the -1. So we distribute that power, and then we have to move. So cross the line, flip the sign, then we're left with 5/1. Okay? If I plug in 0 for x, I have 1/5 raised to the 0 power is 1. And then if I plug in just 1/5 to the first power, that just leaves me with 1/5. And if you want to write that as a decimal, 1/5 is 0.2 as a decimal. So if I draw this graph, if I go a -1, up 5, 0, 1, and now I'm at 1.2. If I connect my dots from left to right, I'm going to be declining. Remember how we talked about if your b value is a fraction or a decimal, it's going to decline, like that picture that we had at the beginning of our notes? That's what this looks like. But now I have to perform a transformation, this plus k, to my y values. So I want to transform or graph the one where y is equal to 1/5 x all plus 1. So that means I'm going to add 1 to my y values and remake a table that I'm going to plot so my x values don't change. And now I'm just adding 1 to all my y values. 5 plus 1 is 6, 1 plus 1 is 2, 0.2 plus 1 is 1.2. So plot those points, -1 up 6, 0 up 2, and then over 1 up 1.5. So we're just a little bit above that red line, up 1, right? So what's my domain and range for this function? Well, I'm not restricted on the left or on the right. So that means that it's all real numbers, or -infinity to infinity. And then my range is going to be dictated by that asymptote. You guys, when I talked about asymptotes, it's never crossing that line, right? So my red, I kind of drew this a little funny, but my red line never crossed that y equals 0. But now that I moved my parent table up 1, this plus k, that means that my new line of not crossing, and I drew this poorly, so I'm sorry about that, is y is equal to 1. My blue graph should not ever be crossing y is equal to 1, okay? So that means that that's what my asymptote is. Y is equal to a +1, and that's where my range starts. So I'm going from that line, but I'm never touching it, so it's going to be a parentheses, all the way up to positive infinity for forever. So it's 1 to infinity. I understand that you guys may be confused on the asymptote, domain, and range for these pictures and these graphs, but we'll talk about it more when we come back to class. So I just want you guys to make sure you get all the vocab written down in your foldable, and then example 1 and example 4. So one example of exponential growth and one example of exponential decay in your notes. So that's all I'm asking of you to do in these notes in this video. And then when you come back to class, we'll do example number 2 and example number 3 together. So I want to thank you for taking such good notes, and I'll see you soon.